Mike's crazy model. Okay. This is more of a thought experiment. This is not something that's published. I wanted to give people context for errors in soil moisture estimation. And it's very simple. And so we're looking at like 30,000, 100,000 feet in the air. We're in space looking down. So we'll see how this goes. It's short. So here's a network. Among these networks, there are many state networks. I focused on one network in particular, the Climate Reference Network, CRN. It's across the entire country. It's done fairly uniformly, whereas SCAN has a lot of preferences for certain locations like Utah and Alabama, because there's a propensity for the stations got turned over. So I want to just have something completely uniform. I use CRN here. So what's the soil moisture like today? Can be a question you ask. And I could say 22%. Do you think I'm right or wrong? You're like, well, it depends on where you are, right? Depends on what time of year it is, if I said today. But if I told you that the average across a 10-year window across all of CONUS, the answer is 22% average. That is a really dumb model. That's super easy, though. You know how much it cost? $0. It doesn't cost $1 billion. It doesn't cost even a couple 100,000 for a network. It's 22%. So this is the average for CRN across a 10-year period, and that's going to be what I'm going to be referring to and working off of. I took those, it's about 90 stations. I computed each station's average, and I calculated I took each station's average across the 10 years, and I plotted them. And there's two stations that are really wet. You can see them on the far left, and you can see that this is a relatively straight line, which is a little interesting because it's not very normal looking. It's more uniform looking, right? It is a good job for CRN. You've distributed yourself uniformly across the country, both spatially and soil moisture wise. This is kind of thinking like, well, in Arizona, it's drier than in Louisiana. And this is being represented here with this average. We also see that we go all the way down into, 5% average on the far right. And we're way up in that, probably something wrong with the above 50% on the far left. But this is a little bit confidence building. I don't see anything super crazy, but it lets me know what I'm looking at. Most people don't plot this ever about their own network. This is the first time I did it, thinking about what is my average across my network. So then I decided, what if I said 22%? How am I doing? And with that estimate, what is my unbiased root mean squared difference? Call it error. If you consider your network true, then this is an error. And we've heard a lot of magnitudes of error thrown about. Oh, my model does this, or my model does that. I have a 2% error. I have a 4% error. Satellites, their goal is 4% or 0.04 cubic meter per cubic meter. If I were to use just 22% moisture, how am I doing at each of these stations? These 90 plus stations at CRN that I'm using that had a good enough data set during that time period. Well, that first green line shows me that for about 30 stations, I have a sub 4% error. Just one number. I can estimate my number at that station and be compliant with the satellite, with a super intelligent system, many satellites. What if I go to 6% error, which is a lot of people will say, I have a model and it hits 6%. Great. I can, with one number, hit 60 stations and be sufficient, which is 2/3. 60 out of 90 is 2/3. 2/3 of my sites, I'm good by most modelers' standards. And again, what's my number? 22%. Mike's super stupid model. So it's actually a 2.19 cubic meters, 10 years of data. This is soil moisture at the surface. If I were to, the overall root mean squared error across the network of CRN, though, is more like 11.7%. Not great. No one's going to write home about 11% error. That basically means that's a Nash-Sutcliffe. Don't want to go in this. Nash-Sutcliffe of 0. right? It means I'm just as good at using my average. The model provides me no information. We're starting at 11 or 12%. Okay. So if you do worse than 12% and you send me a paper talking about how great your model is, guess what? I'm quoting this number and saying I would do better off giving you a straight number. Your model is not really that great. And I've done that. Sorry if that was your paper. So, but now we know where we're starting. 12% is the worst I should be doing. If I'm not hitting 12%, if I'm not doing better than 12%, I better go back and look at what I'm doing. And that's for CONUS. You've seen, I showed, that's the entire range of soil moisture conditions from very wet to very dry, all of it together at once. Now, if I'm all in Louisiana or all in Idaho, know that I could probably do really well in Idaho. You know why? Because that's all on that dry side. The drier you get, the less dynamic range you have, the more accurate it is to just give me a number because you don't have that huge sweeping range of moisture conditions. You'll actually see this in a lot of Cal programs. They kind of like put in a lot of, oh, semi-arid. Great. I can give you a fantastic estimate of the Sahara Desert too. Is that really useful? I don't know. But this is a super dumb model. Just one number. What if I used a monthly ensemble mean? So every month I know that there's this time over every month, and I just instead of 22%, I had, it's drier in winter, wetter in summer. I still am at 11%, 11.3% here, monthly ensemble average. That's not great. Basically, I'm doing nothing. I'm adding no value here. But what if I use each station's overall mean? This gives a sense of that station's locality and its own individual performance. I can get it 5.7%. Just knowing where I am. One number throughout the year. For 10 years. Just saying, oh, Louisiana is always wet. Their number is 30%. I can hit below 6% error just from one number. So that's like a spatial, that map is a spatial map. And I just say at all times, this is my estimate for soil moisture at this location. That's a spatial map, constant in time. What if I had a monthly mean for each station? I always get this wrong. I just did this yesterday. I can get to 4.5% error. Even a little better. And what if I use that station's, don't ask me this question because I can't remember what that one's for. Go ahead, John.
No, I was going to ask that's estimating that month's, your last example, estimating soil moisture within that month. So you're saying that month's average at that station you could estimate.
So I have to say I cannot answer that question right now because in my head, I can't remember what that second to last line is. I know what it is, but I lost it. The thing we're talking about right now, let's go to the last line. That's the one that you're thinking, which is every station's own monthly mean. What if for every location, I have a number for each month? So I have 12 maps, 12 spatial maps, one for January, one for February, one for March. That's kind of the most advanced I have, a temporal and spatial map, but it's still a constant number for that month. And month is just a calendar, right? It's not taking into account rainfall or anything. That model gets me to 2.4% error. That is kind of scary. Now I'm cheating. No one's called me on that yet. I'm cheating because I'm using my own data. I'm using the data that I'm computing on. I'm not using an estimate from something else. I'm using the actual raw station data. That's the best I can ever do. I'm training on myself and testing against my own number. But I'm admitting that, right? I'm giving you an idea of this is what as best as I can possibly do with these simple numbers. This is a little combobulated here, but this is my last slide. This is my overall number. So how well can I do with an instrument? An instrument error tends to be about 1% error. If I have three instruments that are the same batch number out of the factory, there's less than a 1% error between them. If I put them in the same exact soil, a meter apart, that's only a 1% error. If I were to then calibrate that for the soil and make sure that my magnitude's right, that's about a 3% error to local soils. As we've heard, rock wool, fantastic, perfect, because it's easier than soil. Well, soil is tough, and soil, I can usually get, I can get below 3% error, but 3% is about average wherever I've been. And there's a lot of documentation about that. 4% error is a passive satellite target. 6% error is an active satellite target. We're right in that realm of monthly averaging. So the numbers that we're comparing to, the Nash Sutcliffe at the top is 11%, 12% error, 0 value to that model. We're down in this local monthly average. That's hard to do. CONUS monthly average. That is a mislabel. So we're all fighting around in this 4 to 6% error. We want to make sure we're doing better with any model or map we make, better than just a monthly average. And there's some, when people always ask me, is this data right? Does this look right? I can say, I can look at it because I've seen a million time series and I go, wait a minute, let's think about this simply. And I'm thinking about obviously this very simply. Well, is it drier in winter? Is it wetter in summer? When is the rainy season? I'm asking myself these questions. That's my quality control. And I want everybody to remember that as you're going through. Some people forget that when they get a number back from their model, like, oh, great, I hit a 4%. Well, what does that really mean? Let me compare myself with a Nash Sutcliffe or some other metric besides just unbiased RMSD. Hopefully I convinced one or two people.